All right, so last time we talked about type 1 and type 2 errors, effect size, how to use SciPy stats to run t-tests, and interpret those p-values from those t-tests. And that's all well and good, but today we're going to come across like a scenario where effect size isn't going to be good enough and we need to do a power analysis. And so that's what today's all about. So today we're going to, by the end of this, you should be able to explain the relationship between effect size and power. You should be able to interpret power on a given hypothesis test. So that's nothing, or rather maybe like a scenario, maybe not a test, but at least the scenario that you're testing. Hey Matt, I went ahead and just started recording all that good stuff.
Yep, that's good.
Awesome. All right, so for the outline, we're just going to work through an example of hypothesis testing. We're going to calculate power and discuss its importance in hypothesis testing, and then we'll do the activity that I have planned. Okay, so let's look at a scenario where we have a control group and an experimental group. So for this one, we're going to use Q1 control and Q1 experimental. And let's plot these two groups against each other. So we're going to look at their histograms. And here we go. So based on this, does it look like there's a difference between the means of these two groups?
Yes.
You say yes. Jacob, what do you say?
Looks almost close, I'd say.
Yeah. Yeah, so the distributions look similar, but the means are a little different. One of them is kind of like over here, and one of them is over here, right? Like where they peak. So the means look different, though there's like an overlap in these two distributions. Let me just run that. Okay. So the first thing we want to do is set up a hypothesis test. We're going to be using an independent t-test. And the null hypothesis is that the mu of the control equals the mu of the experimental. The alternative is the opposite of that, that they're not equal. And I'm going to use an alpha value of 0.05. And then here we get we get our p-value of basically 0, which means what? Do we reject or fail to reject our null hypothesis?
Reject.
We reject the null hypothesis. So there is a difference in the means of the groups. Okay. Cool. So the next thing that we want to do is calculate effect size, and we're going to do this. We're going to create these two equations, and then we're going to go ahead and calculate the effect size of our Q1 experimental and Q1 control. Now, I do want to say this on effect size real quick. I didn't mention this last time, but if you notice, this can return a negative number, so you should put what you think is the bigger mean first, and it will return a positive number. If I switch these around, like say I do this instead, it's going to be negative. So you can also just be safe and do an absolute value here. And that way you're always going to get a positive value of the effect size. But if it's negative, what that means is that this one has a smaller mean. The first one's a smaller mean than the second one. So I just want to cover that in case you come across negative effect size. You should just switch the two around so it's positive. I'm going to put that back the way I had it. Oh, something up here. Oh, yeah. There we go. All right, cool. So we get an effect size of 0.82. Now, what kind of effect is that? Is it small, medium, large?
Medium to large.
It is like a medium to large. I would just go ahead and call it it's a pretty large effect. So whatever experiment we were running, we did see like a large effect on the mean of the two groups. And this is all good, except the issue is that like effect size itself isn't something that you can interpret from hypothesis test to hypothesis test. So if we conduct another experiment, we look at that effect size, we can't compare our effect sizes because we could have had a different number of samples. We could have picked a different alpha value. We could have, like if you change something, your effect size basically is no longer consistent. So what we do is we have something that's called power, and power is a great way to kind of talk about a similar. It's really looking at your type 2 error rate, like the inverse of it. But what's great is that it's scaled. Like it takes into account all the observations you're running. It takes into account your alpha value. It takes into account all the things that you could change, and so you can compare your power between experiments much easier than you could your effect size. And here, power is equivalent to 1 minus type 2 error, and it's scaled across all the problems, which is great for interpretation. So how do we calculate power? Well, we're going to import this library from stats models. And I went ahead and just did help on it so we could read the documentation. And if you look, here's what it does. It solves for any one parameter of the power of a 2-sample t-test. So the parameters that you can have are effect size, number of observations, alpha, power. Ratios, don't worry about that. That's auto-calculated. You don't have to do anything there. So basically, if we want to solve for power, we just have to provide it these three. If we have maybe these and we want to solve for effect size, we just feed it observations, alpha, and power. Or you can feed it effect size, alpha, power to solve for observations. So basically, it'll just solve for whatever one thing is missing. The effect size is just the Cohen's d value that we calculate. The observations are the observations of sample 1. I usually just do the control, but I don't know how much that matters because the ratio is kind of what it ends up looking at anyways. The alpha is just usually 0.05, and then the power is what we're going to calculate. So we'd actually, and it's 1 minus the probability of making a type 2 error. Now float. Ratio, the number of observations in sample 2 relative to sample 1. So the default is 1, which in this case they're all 1, but basically you can set that if that ratio if you really need to. And then it just returns the value that you're searching for. Any questions on that? Okay, so we're going to prepare our variables. So I just went ahead and set effect size, knobs 1 and alpha equal the effect size we calculated earlier, the number of rows in our control group, and then 0.05. Any questions on this? Any questions at all? Have y'all ever seen this before where you set a bunch of stuff equal on one line? All right, just making sure. I don't think I ran this cell also, just in case. Okay, I did. But you never know. All right, cool. And then we can run this. We'll call this knobs 1. And we'll go ahead and run that power. And we get a power of 1.0. So since the power is 1.0, that means our type 2 error rate is 1 minus power, which is 1 minus 1.0, which is 0. So it's saying that we have a type 2 error rate of 0. Now, if we just go back, does that look like a type 2 error rate of 0, looking at those distributions? Well, we would have to cut off on our control. at some 0.05. We'll just say that's the critical value just for the sake of moving forward. And then we would take the area of our experimental that's behind this. So it would be kind of that area right there. So it doesn't look like it's 0, but it's giving us 0. Why? Does anyone know? No. I thought somebody was going to say something. So it's doing that because the means are far apart. Like they're far enough apart to cause a big effect. So you have to be really careful. Like I'm just telling you, all these things are, you have to always be careful when you're interpreting these. Like we probably don't have this as a type 2 error rate because there's area under the curve, you know, but it's calculating that because the means are fairly far apart. If I change my sample size or alpha or effect size, my power would change. What do you think would happen if I decrease my alpha? Would my power go up or down? Any ideas? It's the inverse of your type 2 error. So if we decrease our alpha, what's possible? Like what's going to happen?
The power will go up.
Why will it go up? Why are you saying that?
Because it was the inverse of the alpha.
It's not the inverse of alpha. It's the inverse of your type 2 error. Yeah, so let me just like draw that out real quick. Can I have an example?
I'm eating, man. I couldn't draw it out here.
You're good. Don't worry about it. So like, let's say this is our critical value. Our type 2 error would be the area of our second curve that's behind that value. So if I decrease my alpha, what's going to happen to my type 2 error?
It should decrease.
Okay, and why are you saying that?
Because if you're decreasing your alpha, then you're moving your critical point like further to the right. So I guess it should increase, actually.
Yes, it does increase. Yeah, if I decrease it, my alpha moves, the critical point moves to the right, which means I've now opened myself up to more error, right? So that's good. And you'll see that. I don't know if it's going to actually show decrease here because the means are fairly far apart. Yeah, it doesn't really show it. We might need something like super, yeah, it's not going to do it. And it's just because the means are so far apart and our samples are, it's a big number. It's 100. So that's why it's going to have a hard time doing that. But yeah, yes, it should, in theory, decrease. Okay. So here's the summary that I would write. For the hypothesis test, we reject the null. I would also state it here. I just didn't type it for the sake of not having room. I would say the means between the groups are different. I would state the effect size and just kind of write a blurb about that, and then write about the power analysis. So in general, what can we say about power? Given that it was 1.0, effect size was 0.82, what's one thing that in that very brief presentation that you learned about power, if anything? You can say nothing if that's the case. Anyone? Nothing?
It tells us that we can trust the t-test.
Okay. Then
like a test on another test.
Oh, okay. So we can compare t-tests. Is that what you're trying to say?
Yeah.
Yeah. Yeah, you can compare like experiments. I don't know if you were here for that. Is it Liz or Beth? Which one do you prefer? Or is it Elizabeth?
Beth.
Beth. All right, cool. But like the reason that we even have power is because effect size. So whenever you're looking at effect size can change from experiment to experiment, but like you can't, like if it goes up between experiments, you can't interpret that as an actual increase because it can go up for a variety of reasons. Maybe you have more observations. Maybe the standard deviation changed a little bit. Like effect size is a really hard thing to compare between experiments.
So this power test is kind of like a z-score in a way. It allows
Yeah,
us to compare.
it's like a standard number that you can use between experiments for type 2 error rate. Right?
Gotcha. It also seems like it's a validation as well.
Yeah, it could be seen that way. I don't know. I'm always confused whenever I see anytime I see good numbers like 1.0, it makes me raise an eyebrow and I feel like I did something totally wrong. And that's usually the case. So like you always have to never get too hopeful is the lesson. Like something could have happened. But yeah, it is a way to compare like experiments. So it's a good use of it. Similar to a z-score in purpose. Cool. All right, so here's the activity. You're going to conduct power analysis for the given problems. You're also going to have to do the hypothesis testing and the effect size calculations. Whoops. Here's your data frame. They are labeled for you. So there's control and experimental for Q2, control and experimental for Q3. In Q2, there was an experiment that was run on Facebook to determine if adding a button increased the engagement on the timeline or newsfeed or whatever the heck it's called. Please conduct the proper test, get the effect size, and do a power analysis to determine if there is an effect. Your work's going to go in that cell in the notebook. And then for Q3, basically just, I didn't think of a scenario, couldn't think of a creative one in time, unfortunately, but run the experiments between the control group and the experimental group as well. And then I want you to repeat Q3, but this time I want you to take a random sample from each group and do the same process and see if there's a difference. So the control sample is done for you. This is how to take a random sample of 30 individuals from the control group. You're going to have to write it for the experimental, do the entire process for those two groups, for those two samples. Okay, and that's it for me. Any questions before you begin? All right, so you should have this notebook open. I'm going to go ahead and stop recording. I don't see the button to do that. All right, cool. So for this first one, you just have to use these two columns of data, the control versus the experimental. So you can run it and get your p-value. You can calculate your effect size similarly. And then you can do a power analysis, getting your effect size. There's 100 observations, and then an alpha value of 0.05. That'll give you power. And so that should all give you a p-value of less than 0.05, which means we reject the null hypothesis, so the means are different. We have an effect size of 0.47, so light to medium effect. We have a power of 0.91, which means our type 2 error is about 10%, roughly. We have a 10% chance of making a type 2 error whenever doing this. So are there any questions about this right here? So this is great, all well and good. You can do the same one for question 3. It's basically the same workflow. You just got to change this to Q3. You're going to get these numbers. We get a p-value less than 0.05, which means you reject the null. We get an effect size of 0.5, which is medium. We get a power of 0.96. But this is the big one that's pretty different. So here we're taking random samples of the control and the experimental group from before. And we're doing 30 samples. And now whenever we calculate everything, notice that in my solver, I have to put my effect size. I have to put the number of samples, which is 30. And then I have to put my alpha value of 0.05. And my power went down a lot. Something funky just happened? No, there it is. Okay. I don't know what that was. But yeah, it goes. So the power that I got, I don't know if something just happened with my random seed. I thought I set it. I might not have set it. But I got like 0.1 or something. It went down though. That's like something that you should have noticed, is that your power value is less than it was before. And I want to talk about that for a little bit. These are discussion questions that I have, but we're kind of going to start talking about it. But did anyone do this and they notice that at all? Okay. So now we're going to kind of talk about why that happens, and I think you're going to get a better understanding of what power is trying to tell us. So in this case, we have an effect size of 0.92. I don't know. Let's run this. Let's just say we have an effect size of 0.53. So we're going to solve for power. Alpha is 0.05, and this is 0.53. All right, so notice the effect size is measuring kind of like the distance between our two means right here. Now, if I change my sample, so earlier I had a sample of like 100. Well, my power is 100% now, right? There's no room for type 2. Why? Versus like if I only take 30 samples. Now I have room for type 2 error. Why? What's going on here? Why do you think increasing samples decreases your type 2 error?
Because you're getting more towards that like law distribution or whatever, where the more samples you get, your data becomes more normal on the like means and the stats on it.
That's definitely part of it. It's definitely, don't think of it as getting more or less normal. Like it's fairly normal now. And if I increase this, it's still just as normal. But what's changing as I increase it?
For me, what changed was the range of data. Whenever we took the smaller sample size, the range of it was less.
The range is less. Okay. But if I do that here, so if I do 30 here, I go from like 0 to 1 point something. And if I increase it up to 100, now I'm strictly between like 0.2 and 0.8 something. So can you elaborate on what you mean whenever you're saying like when you take less, it increases the...
So whenever you take less data, you have a smaller sample size. It's less representative of the population. So you don't get as much of the extremes as you do with a bigger sample size. So that means that the range of data that you're viewing at the end is less than it is whenever you have more samples. And I think that's probably what causes the power to decrease, is because what you've discovered isn't necessarily true to the population.
Okay. You're saying a lot of things. Some are very correct. Some are, I don't know if I would say that correct or incorrect. They're things I haven't thought about before. Yes, if we get more data, we understand the population more, right? Like just sheer numbers inform us. That is true. But if we get more data, like literally look at the blue distribution, what changes as I increase it? Matt, do you know what I'm trying to get at?
You're just trying to say that the graphs kind of get taller and skinnier,
Yeah.
and they kind of get further apart, like there's more distance between them.
Right, but the distance between the means isn't different, but the distance between like the full areas, like
The
where
edges, yeah.
right, that overlap changes. But why? As I add more, why is it getting thinner? What's changing as I add more data if it's getting thinner? What dictates the thinness and thickness of a normal distribution?
What are the two things that affect a normal distribution?
Yeah. What define a normal
The
distribution?
mean and
I guess you're trying to get at your standard deviation goes down.
Yes. Yeah. So as you get data, do you remember those degrees of freedom? This is where they matter. Because like if we increase data, our variance is just gonna go down. Like we're gonna have a thinner graph or a thinner distribution. And so by nature of just numbers, when you have a smaller number of which you can't extrapolate this to what you were kind of alluding to, Beth, but basically if we have a small number, we're open to more type 2 errors. But you can also think of that as like we haven't observed this enough to really know, right? Like we've seen it some small number of times. But if we have this many observations and we're still getting a normal distribution, well, now all of a sudden, like we have more clarity on like the actual phenomena. But it does lower our variance. That's kind of what happens, which is why like you have to find the sample standard deviation, right, and not the population standard deviation. You need to use those samples, those degrees of freedom. But yes, that is the big takeaway. Is like if you change your sample size, it actually changes your power. So smaller gives you smaller power. Now let's say we have a sample size that's consistent at 30, and we change our effect size. What's going to happen if I increase my effect size? Is power going to go up or down?
Your power should increase.
Okay. Jacob, what do you think? Brendan, type what you think. I'm curious.
Decrease.
Okay. Okay, let's see. So we increase our effect size. So if we increase our effect size, our power went up. Because what moves as I increase my effect size? What does it change about this distribution?
The means get farther apart.
Right. The means get further, which means there's less overlap. Less overlap means more power.
Gotcha.
Right. Because if you don't have, like when you don't have a lot of power, you have a lot of uncertainty. And that's what uncertainty looks like, just this massive overlap between the two. So the less overlap, the more certainty. And that's why they call it power. Cool. Well, thank y'all. I am done talking about power now. We're gonna move on to ANOVA testing. So I'm gonna hand it off to Matt.
Thanks, Raphael. All right, so if you want to open the ANOVA notebook, we're going to be in that now. I'll give you a second here to get it open. All right, so ANOVA, or analysis of variance. So ANOVA lets us, we've been doing hypothesis testing with two groups basically, and now ANOVA lets us go in two groups. So are the means of different groups the same or different? And here's a little cartoon to kind of show that. So if we have three different groups, different distributions, how can we say they're all actually part of the same group overall? So hypotheses for ANOVA, assuming that we have more than two groups, so we have groups 1, 2, 3 up to K, the null hypothesis is that the population means of all those groups are equal. And then the alternative hypothesis is that at least one is different. Notice the wording on that, it's at least one. So it doesn't matter if 2 of them are, if 3 of them are, if all of them are different, as long as one is different, that's our alternative hypothesis. So for an example here, we have a situation where a company is trying to optimize the performance of their data scientists. They come up with 4 different control groups, so they give them different substances. They have them work on building a model, and then after the time's up, they check the accuracy of their model and see how they did. So we're looking to get a 95% confidence level. Here's the 4 groups. So the first one's given coffee, the second's given alcohol, the third's given chocolate, and the last one's just given water. So here's the data for it. I just put it into lists for each of the groups, and they're just going to be labeled A, B, C, and D. All right, so there's a really easy way to do this. I'll show you the easy way first, and then we'll dig a little deeper. So you just, from SciPy stats, you can just do, it's an F test one way, and then you can pass in your 4 different groups there, and it will give you what's known as the F statistic and the p-value for that statistic. So if we go ahead and run this and print this out, all right, so we have our F statistic here. It doesn't really mean anything to us yet, but then we can see our p-value is very small. It would be less than the 0.05 for our alpha. So we could, in this case, reject the null hypothesis and say that there is a difference in the groups. So an F distribution is unique by 2 different values. It's the degrees of freedom on the numerator and degrees of freedom on the denominator. There's a lot of math involved that we're not going to get into, but basically the degrees of freedom for the numerator is of the groups, and for the denominator, it's of all the subjects total. So if we have the number of groups and then the total number of subjects, so in our case, we had 4 different groups for the 4 different substances, and then each one had 10 participants, so we have 40 total subjects. So the degrees of freedom of the numerator is just the number of groups minus 1, and then the degrees of freedom of the denominator is the total number of subjects n minus the number of groups. So let's see here. I'm gonna pop this out into its own slide. All right, so we're gonna plot an F distribution now to kind of see what it looks like. So this is the general shape of an F distribution. You'll notice it's not symmetric. It kind of is skewed to the left, and it decreases as you move to the right. It has a really long tail, or it's skewed to the right. It has a really long tail on the right side. So this is the F distribution for our question at hand, because the degrees of freedom of the numerator is 3, since it's our total number of groups, 4 minus 1. And then we had 40 total subjects minus, this should actually be 36, minus our number of groups. So it's still pretty much the same shape. So now we can kind of compare different F distributions with different values for those degrees of freedom, numerator and denominator. So I just kind of switched them around here. And if we plot that, you can see kind of how they change depending on the differences in degrees of freedom. So like if you look at the red and the green, they both have the same numerator degrees of freedom, but the red one has a much higher denominator degrees of freedom, and you can see it makes it much taller. And then also, it seems that the numerator degrees of freedom kind of makes the F distribution jut out from the left a little bit, so it kind of shifts it to the right. So another thing to kind of think about is that ANOVA is actually just multiple linear regression. To give some intuition on why this is, I'm going to make a data frame just of our data for this experiment. And then I'm going to add category codes for each of the groups and then dummy variables, just so it's kind of easy to work with and graph. And now I'm just going to calculate the means of each of the groups. And then I'm going to plot those means and do a regression plot. So if we go ahead and plot that here, so we can see I sorted the groups in terms of increasing mean, just so this example works. But you can see that there does seem to be some change as we move across the groups. If they were all the same, we could kind of expect this to be a line straight across because they would all almost have the same mean. All right, so another way then to find the F statistic and to run an ANOVA is to build out a linear regression with our different groups. So this is just using stats models OLS like you did in the first module, and then our 4 different groups. And if you're doing it this way through the stats models API, you don't want to forget to add your constant here. If we go ahead and run this and print out our regression table. All right, so we can see our coefficients here, and then up in the top right, we have our F statistic, which was the same as what we got before using the SciPy library. And then we have the p-value for that F statistic all right here. And then just to show you that it works, if we print out our means again, if we take out the constant and just run the OLS again, we can see that the coefficients are just the means for each group. So that kind of gives you some idea of why ANOVA is linear regression. So if you remove the constant, the coefficients are just the group means. All right, so now a third way to do ANOVA, it's still within stats models, but it's using the formula API. So you have to write it out in this formula format, but it allows you to access the ANOVA table, which you can't get the other way. So if we print this out, we see we get a really nice table. It has our degrees of freedom. You can see that the first one's what would be the degrees of freedom for the numerator, and then degrees of freedom for the denominator, which is the residual degrees of freedom. And then again, we have the same F statistic and the p-value for that here. So 3 different ways to run ANOVA, but you get the same result with all of them. And that's just to compare to our earlier results, and you can see they're the same. All right, and then just to kind of hit this home, so what I did was I took 2 of the groups that were similar, groups A and C, and I kind of just made the groups B and D copies of them. And then I plotted the means, and you can see that now it's like more of a straight line. So now if we do an ANOVA on this new data set, we can see that our F statistic's very low and our p-value is very high. So this would cause us to fail to reject the null hypothesis, and we'd have to say that there is no significant difference between the groups. All right, so we learned there's a difference in those groups, but where is it? It didn't really tell us much. It didn't tell us, oh, the caffeine helps better than just water. So how can we kind of dig a little deeper and figure that out? Well, that's where Tukey's HSD comes in. HSD stands for honestly significant difference. It's what's known as a post hoc test. So you start with ANOVA. If the ANOVA gives significant results, then you can do a test like this. And it basically shows you where the difference is. It will do a pairwise comparison between all the different groups. So to see how that works, we can import it here. We can get it from stats models through this import command. And then all we have to do is pass in our target variable and then our independent variables and print out the summary table. So you can see on the left, it compares each group to each other group. It shows the difference of the means, the p-value for that difference. And then on the right, just whether or not you could reject the null hypothesis there. So for example, this is telling us that there is a significant difference between groups A and B, between A and D, between B and C, between B and D, but not between A and C and C and D. So to view this graphically, you can do the plot simultaneous off of those results. And I'm going to have to go back out and make this a separate slide because it doesn't fit. All right, so this is the graph we get. So we have our different groups here. kind of the way to read this is if you would draw a line straight down and it passes through two of the groups, then you can say that they are, you can't say that they're different. You can say that statistically they're kind of the same. So for example, group B was if they were given alcohol, so we can see that it's statistically different than all the other groups. And just to confirm that, we can go back up here. And so for C, let's see, or I mean for B, all the ones that had B as one of the groups, we rejected the null, and there was a statistical difference there. So that's kind of the simultaneous plot you can view off of your Tukey results. So to summarize, ANOVA tells you there's a difference. Tukey's tells you where the difference is. But wait, why didn't we just do multiple t-tests to make all those comparisons between the different groups? Well, let's say these are the p-values we got for testing all 6 of our possible combinations. So we can see they're all 0.05 or less, so we would reject the null in all of them. But since we have 6 of them all together, if we wanted to find the total odds of all of them holding true, so basically, like this first one saying there's a 5% chance we're wrong, the second there's a 4.2% chance we're wrong. So if we would calculate the total probability of not getting any of these wrong, we could do it this way by taking 1 minus all of these probabilities and then multiplying them all together. So if we do that, we can see there's actually only about a 76% chance that all of these will hold true and we won't have any type 1 errors. So then if we were to double the number of pairs we have from 6 to 12, keeping kind of the same, they're all about 0.05, then we can see that probability drops down to 58.6%. So when we have a bunch of comparisons and we're comparing the p-values, the probabilities kind of add up in a negative way, and it kind of puts kind of a dark cloud over our results, and we can't really say for certain that what we've observed is the actual case, because when the probabilities add up, there's more and more of a chance that there's an error somewhere in there, and that's known as the family-wise error rate. So what Tukey's does is actually account for that. It doesn't just run multiple t-tests. It accounts for that error depending on how many different pairs of comparisons it makes. All right, so what if the company also wants to consider the level of the data scientists in their analysis? So whether they're a junior, mid, or senior level data scientist. Here's the data for the different levels, J for junior, M for mid, and S for senior. So we can go ahead and store that there. This is where a two-way ANOVA comes into play. This is what allows us to compare groups that are split by 2 independent factors. So now we're comparing the different substances they got, and we're comparing that to the level that they are as a data scientist, and then seeing what effect that has on their performance in building a model. So for two-way ANOVA, the hypotheses, yes, there's more than one. It's a little more complicated. There's actually 3 null hypotheses and 3 alternative hypotheses for two-way ANOVA. The first null hypothesis is just for the first variable that all the population means are the same. Similarly, for the second variable, all the population means are the same. And then the third null hypothesis, it's kind of hard to write out mathematically, but basically it's saying that there's no interaction between A and B. So if B is changing, it doesn't really have an effect on A. So then the alternative hypotheses are just kind of what we saw in the one way for the first 2. And then for the last one, it's just that there is some interaction between A and B. All right, so now we can just add our levels to the data frame that we have. And we can use stats models ANOVA to run a two-way ANOVA. Let's see here. We have it there. So you can see at the end type 2, that's for two-way ANOVA. And then to make it an interaction term, you have to do this here in the formula. So group times level. This will basically, you'll see the results here in a second, but it'll basically give us a group a level, and then an interaction term, group level. So then this shows us the 3 different F statistics and p-values for 3 hypothesis tests. So you can see it looks like we would reject the null for group. There's a difference in the groups, but there's not necessarily one in the level. But in the interaction term, there is some interaction between group and level. And that just kind of summarizes that there. All right, so now we can do a Tukey's analysis on this. You can see it's a lot larger chart since we have so many different pairs we can make. But the way to read this is basically, so this is junior developer or junior data scientist who had treatment A versus mid-level data scientists who had treatment A, so on and so forth. You can see some of them were able to reject the null and say there's a difference, some were not. We can again plot the simultaneous graph here. You can see that for treatment B, both junior and mid-level kind of seem to be significantly different than the rest. And then to further see this difference, we can plot what's called an interaction plot. So on the x-axis, we have the level. So 0 is junior, 1 is mid, and 2 is senior. And then we can plot the different treatments. So we can see that for treatments A, C, and D, there's not really a change in accuracy as we move across the different levels. But for treatment B, which was the alcohol, there is a difference. So the accuracy seems to be lower for junior and mid data scientists, but much higher for senior data scientists. All right, so to kind of bring that all together, we're going to do a fun activity here where you're going to come up with your own hypothesis test and run either a 1 or a 2-way ANOVA to test it out. So the scenario is a company's been testing out ad configurations on YouTube videos. They've been playing with a bunch of different things like where the ad is at in a video. So at the beginning, the middle, or the end, where the button to go to their website is on the video, the color of the background music, and the category of the video that the ad's placed on. So like a gaming video, a beauty video. And they've compiled all this data in the CSV file here that's in the repo. So your task is just to pick one hypothesis test, taking either 1 or 2 of the variables and testing its effect on conversion. And that's the number of people that ended up clicking on the ad from that specific ad. So you have to use either a 1 or a 2-way ANOVA, design and test the hypothesis, and then present the results. So with that being said, does anyone have any questions? No? Okay, I'll go ahead and pause recording then.
Let's see. Okay. So the first thing that I did is I wanted to run a 2-way. So I set up my null hypotheses and my alternate hypotheses where so basically I wanted to see if there was any relationship between the conversion and video type and duration, because those to me are the things on ads that I can like understand. I can understand a video being of a certain type and I can understand it being so long, right? So I set up my data frame and I ran my ANOVA on it, and I noticed that all of my p-values were not less than 0.05, so there was no correlation between any of them. So I failed to reject them all. So I redefined what I was looking at, and I decided to look at the one thing that I hate most in ads, which is background music. And the video location, I hate how it pops up in different spots. I wish all of them were just the same. And so set up my data frame, ran my ANOVA, and I noticed that there was a p-value that was less than the 0.05. So I rejected the first 2 null hypotheses, but I had to fail to reject the interaction between them. And then I ran my Tukeys and got this. And something that I noticed that was interesting was I can't highlight it. If you look at the middle data, like the songs for all of the middle data kind of overlap less than all the other data. So I plotted it in the super fancy graph that Matt helped us set up, and I noticed that classical music was different than all of the other ones. So yeah.
So what would you recommend then based off of that?
I would recommend putting an ad in the middle of the screen with like dance music, because it's the highest. Yeah.
And not classical.
Not classical. Classical people are just going to kind of chill out and wait. You got to get them hyped or annoyed.
Yep. All right, cool. Thanks for that. Jacob, your turn.
Alrighty. I'm gonna scroll down here. So what I did was just looked at the data to see what info was in there. Set up my null to be everything being equal. Well, I just picked the video location and duration, having the same effect or no effect, and the alternate hypothesis of at least one of them having an effect on the conversion. I did the stats ANOVA to compare the video location and duration, and saw, looking at the F statistic at video location had a large impact on that. P-value was pretty much 0 opposed to duration. But looking at duration and video location, it was a pretty large impact still. So I did the Tukey pairwise and look at the summary just to see, and everywhere where we rejected the null, it was a short video was included in all those, and it was either beginning or middle for the ad. Unless it was a real short video, then they were throwing ads at the end. So my recommendations was having a ad located at the beginning of the video to have better conversion. And for duration, if you had short videos, ads at the beginning, middle, or end would have higher conversion, depending on how short your video was. So we can reject the null since the F statistic is medium for duration and large for the location of the ad.
All right, cool. So just on the hypothesis test for that, since it's a two-way, it would be kind of set up like BEST, where you have the 3 different ones. So like the first is that all the groups of the first feature are 0 or are the same. All the groups of the second feature are the same. And then the third is that there's no interaction.
Okay.
Because then those are the 3 lines for that ANOVA table. So then in your case, you rejected the null of the first one. So whatever you had as the first feature, there is a difference there, but there's no difference in the second group, and there's no interaction. And so with that being said, it also kind of goes with what Beth did. Technically, if you get insignificant results on the interaction, you shouldn't do the Tukey test, because the Tukey test means that you already got significant results for the interaction. So you really shouldn't pursue the Tukeys then unless it gave you a reason to do so with significant results on the interaction term.
So
if that makes sense.
If the interaction is greater than 0, I figured it was an interaction since the formula had, 1 times the other equals 0.
So on that, you just want to look at the p-value really. The p-value is for that third hypothesis that there is no interaction. Okay. So if your p-value is less than the 0.05, then you can reject the null and say that there is an interaction.
Gotcha.
Yeah. You don't have to worry too much about the actual F statistic since you have the p-value there. But in general, a lower get you, a lower F statistic will get you a higher p-value, I think.
Okay.
and vice versa.
Okay.
Yep. Does anyone have any questions about anything tonight? Do you like doing this kind of stuff?
Mhm.
I know Beth does.
Hey man, I'm learning to love it.
It's cool stuff. You can test a lot of different things, and then you can, you know, back it up with evidence statistically. So,
Yeah.
and you'll definitely be doing one-way and two-way ANOVA Mod 3 project. So, again, tonight's like super important for project week. So, all right. Well, if no one has any other questions, I think we'll wrap things up there.
Alrighty.